Zoom. Yes, indeed. Hello there, everybody. We
Hello,
are
everybody.
live on everything. I'm pretty sure. You're never sure these days on the internet, but I'm pretty sure, and that's going to have to be good enough. This is OpenCV Live. I'm Phil Nelson. I'm here with OpenCV CEO Dr. Satya Malik, and we'll get started in just a couple minutes with our presentation. But before we do that, we're going to ask you out there, whether you're watching this live or you're watching the recording later, go ahead and drop a comment wherever you're watching on the wide world of Al Gore's internet. We're live on YouTube, Twitch, LinkedIn Live, TikTok, and Facebook right now. And I'm coming to you from beautiful, fragrant Soma in downtown San Francisco, California. And Doc, where are you joining us from today?
From San Diego, California. The weather is beautiful. It's summer here, and it's really pleasant, and the days are long, so everything's really good here.
Yeah, good old Southern California. The burritos are large, and it's about 65 degrees every day.
It only comes in family pack,
That's right. That's right. The size of a small child, as I used to say. Look, we've got folks checking in the chat. Let me go ahead and pull it up here. We've got over on Zoom. We've got Hyderabad. We've got Howdy from New Jersey. We've got Helsinki, Finland. We've got Patrick, who says they're cooking in Albuquerque. I believe that. We've got Virginia. We've got Basingstoke, UK. We've got Sweden checking in. Love to see it out there, folks. Thanks, everybody, for joining us here today. And, of course, as I said, wherever you're watching, go ahead and drop those comments. Say hi. We don't bite, at least not unless you're willing to pay for the privilege. And we'll bring up the best comments here on chat using the Restream system we've got going on now, which I think is doing pretty well. I'm a fan. Speaking of which, let's do a quick throw a QR code up on the screen here. Yeah. Did you know that OpenCV is a nonprofit organization? You can donate to OpenCV by scanning that QR code up there and seeing the various ways you can support OpenCV. We'll talk about that a little bit more later in the episode, but for now, I think we will get started in just a sec. I see over in Zoom, we got a few more people checking in. We've got San Jose, we've got Chicago, Illinois, we've got San Ramon, we've got Moscow, we've got Chicago again. Speaking of various locations that people are checking in from, let's briefly talk about an in-person event we are doing here in the Bay Area this week. Thanks to our friends at Oshawa and Ross, we are going to be at the Open Sauce exhibits. Open Sauce is a huge, thousands of people show up here in the Bay Area every year for Open Sauce. Of all the best and brightest and most fun open source projects will be there, including OpenCV. And I'll just share my screen real quick here so I can show you all what we got going on. Allow to share a window. There we go. Yeah, so Open Sauce is this weekend. OpenCV will have a booth there along with the homies at Ross and Open Robotics. You'll see some familiar faces there. Kat Scott and special guest Ginger Zhang from Hackster.io, the person that runs their awesome competitions. I'm pulling up the info here. It looks like we've got they did assign us a booth number finally. And it looks like we are booth N25 in Expo Hall B. We're right in the thick of it there in Expo Hall B. So please come join us, say hi. I will have the last of the 2025 OpenCV stickers and buttons. We went through quite a lot of them at CVPR this year. So yeah, come get some merch, come say hi, do some glad handing, some hot dog and some grandstanding. We will see you there. I think now is a great time to get started. Doc, why don't you take it away while I take myself off?
All right. So welcome, everybody. In today's OpenCV Live, we are going to talk about a clip Now, CLIP is a vision language model. It is one of the first vision language models which was popular, and it showed us that it is possible to train a single model that encoded vision information as well as text information. Now, vision language models mean many different things, right? So we are going to see what CLIP is capable of doing. If you take two different vision language models, they inputs, outputs, everything's are usually different. But CLIP is one of the first ones, and it is a very important vision language model to understand. It also lays the foundation of how you think about vision language models. All right. So I'm going to share my screen right now. And Phil, if you could show my slides.
Yeah, one moment. Before we get started, I'm going to remind the folks out there that we are taking questions from you in the audience. So please use the Zoom Q&A button wherever you're watching. You can use the the Q&A button on Zoom if you're watching on Zoom. You can use the comments on YouTube or Twitch or LinkedIn Live, etc., because I am your co-host with the co-most, the second banana who's second to none. I'm also your plus one and only. It's Mr. Nelson, if you're nasty. And I'm here to remind you that we're also doing a special giveaway to you out there in the audience later on in the episode. Stay tuned. I will be asking a trivia question based on today's episode, and the very first person to answer that question will win the OpenCV University course of their choosing. All right, take it away, Doc.
All right. So in this presentation, we are going to understand what is CLIP, which stands for Contrastive Language-Image Pre-training. Now, if these words do not mean anything, don't worry about it, because we are going to learn each and every component of this CLIP. All right. So here's the outline of this presentation. First, I'm going to give you an introduction to CLIP, what it is and why is it important. Then we'll talk about contrastive learning in CLIP. We'll talk about CLIP's architecture and training. And finally, we will learn about the limitations and challenges. After that, we will go over two notebooks. One of them will teach you about what are embeddings. And the second one will use CLIP to do zero-shot image classification. Again, if those things do not mean anything to you right now, don't worry about it. We are going to go over each and every one of them. All right. So contrastive language image training, or CLIP, is a multimodal model, which means that whenever you hear this word multimodal, it means that it has more than one mode. So vision is a mode, language is a mode. You could also have speech as another mode. So whenever they talk about multimodal models, it means that they have more than one modes. So in this case, we have vision and text. It is trained on internet scale images and caption pairs. So to train CLIP, they basically took millions of images and their captions. You can see that here you have an image of a man wearing a mask, and the caption says man wearing a blue mask, right? Similarly, you have another image here and the caption is colorful buttons, and so on and so forth. Now, how do how do they get these image caption pairs from the internet? The biggest source is basically this. If you look at an image on the internet, most of them would have an alt text. When these images are embedded in a web page, they have an alt text. And the reason these alt texts are very important is before search engines were able to read images, they didn't have any understanding of the images. People had to manually put in what is inside the image, so that for people who are visually impaired, they could understand. The readers would be able to interpret that image and tell them what that image is, even though they could not understand the image perfectly. And in some cases, in government websites, etc., it's a requirement. You cannot have an image without alt text, because you had to be sensitive to visually impaired people. So and also it became very useful for SEO. So the people who are creating the web page, they had a great incentive to put in the alt text. And SEO, it stands for search engine optimization. And back in the day,
really dating ourselves here talking about this.
yeah, but that was the internet, right? Even now,
Yeah.
These alt text, either they are automatically generated or most of the time
Mhm.
people put in the alt text, right?
And the better social media platforms out there, such as Blue Sky. If you use Blue Sky, you can even go into the settings and have it remind you. It won't let you post images without including alt text, which I think is really
That's
useful because
very
it catches me all the time. And I,
right.
so you just want to be lazy and shoot something out there, and it forces you to think a little bit before you do that. And I think it's good because it also, it's accessibility is, I think, one of the internet's great strengths, and we gotta protect it.
Right, right. That's true. And one of the uses of Clip is zero shot capability, right? It is used to classify images without having any training data. We'll see how it is done in this presentation as well. So, okay, now let's look at the data set, right? What it was trained on. It was trained on this data set, which is not public. It is called Web Image Text data set. This has about 400 million image text pairs gathered from the internet. And again, as I mentioned, that it is mostly, all text or captions. Also, sometimes it gets that information from the context of the image. So some of that text is also used. And the word count, just to give you a size of the training, it is basically about the size of GPT-2. So pretty large, pretty large. But this data set is not publicly available. Now, there are two versions of Clip. The vision part they have two different backbones. So there is, this is a vision language model. So there is a vision part and then there is a language part. The vision part, there are two different options for it. One of them is ResNet based, which if some of you know about convolutional neural networks, ResNet is a very popular architecture or a backbone used in convolutional neural networks. And the other one is a VIT or Vision Transformer based architecture. Now you can see that this training time is not trivial. 18 days on 592 V100 GPUs, right? So maybe some startups can afford it, but most of the people will not be able to afford this kind of compute, right?
Yeah, that's some spicy compute.
Yeah, and then the VIT based one took 12 days on 256 V100 GPUs. Now, keep in mind that this is just the final run, right? People might have done a lot of experiments before they came up with the final solution. This is the final run. So you can easily think that to build this model, they must have spent, at least 5 times more compute than you see here, because this is the final run. All right, so next, let's understand what is contrastive learning, right, and how Clip learns. So think about Clip as having two different components. One is the vision encoder, and the second one is a text encoder. Now think about the vision encoder as a black box, or in this case, you can think about it as a blue box. The goal of this box is it takes as input an image, and the output is a vector. The size of this vector is, the length of this vector is 512. The text encoder does the same thing to a text string. So any length text string can be the input. It would do something, right? Don't worry about how it actually does it, but the output is a vector of length 512. Now, both these vectors are of length 512, and they share, because the vector lengths are the same, they share the embedding space, right? Which means that you can take the objective here is you take an image or you take a text, doesn't matter. If they are the same or they describe the same concept, then the vectors that you get from these things, they should be aligned, right? In this vector space, in this 512 dimensional space, they should be pointing in the same direction. That is basically contrastive learning. And on the other hand, so you can see here that we have the image and its own caption. They want these two things to be together, right? So when we say together, we want to align these two vectors. The vectors are aligned using something called cosine similarity. Now, if you remember from high school, the dot product between two vectors, right? Any vector, let's say And don't worry about 512 dimensions right now. Think about 3-dimension. So you have 2 vectors in 3-dimension. And if you take the dot product between the 2 vectors, it is basically the magnitude of A times the magnitude of B times the cosine theta, right? The cosine angle between them. So if you manipulate the equation, see that the cosine theta between 2 vectors is essentially A dot B, which is the dot product between the vectors, divided by the magnitude of the vectors. And as you can imagine,
For the Americans out there, high school is a little bit different in India.
okay, you didn't learn this in high school?
Not really, no.
All right. All right. So I can't believe that, but okay, I'll go with that. So now you have, now imagine, right, when the angle between the 2 vectors, right, A and B, they are aligned, which means the angle is 0, cosine similarity is 1, right? Because cosine theta is 0 is equal to 1. And if they are 90 degrees apart, the cosine similarity is basically 0. So things which are aligned will produce a high cosine similarity. In this case, the goal of the vision encoder and the text encoder is to produce these vectors if the if the image and the text match, they should have high cosine similarity. And if they don't match, for example, here we have an image of a button, right? And the text says man wearing blue mask, and they produce 2 different vectors. And if you look at the cosine similarity, it is 0.10. In the previous case, it was 0.91, right? So this is the kind of system we want to build, which maximizes the similarity between an image and its caption and minimizes the distance between any image and other captions. Okay. Now, the same thing you can see in this view also. So I'm showing image using a blue dot and its caption using an orange dot, and I've normalized the size of the vector, right? So you can see that the image and its caption, they are together, and an image and other captions are far away, right? So this image, this blue dot, is far away from all the other orange dots. Similarly, a caption is far away from all other images other than its own image. So this orange dot is close to its own image, but it is also far away from all other things. So there are 2 pieces: image text similarity, which means that for an image, we want the text, the caption, its own caption to be close, and it should be away from all other captions. And then we have text image similarity, which means that for every caption, we want its image to be close, but all other images to be far away, right? So you can also see this in this kind of a diagram where we have a collection of images, right? I1, I2, I3, and then we have a collection of captions, T1, T2, Tn. And then if you take the dot product, right, between these 2, we should get a dominant diagonal matrix, which means all it's saying that these things should be very high and the off-diagonal elements should be very low, right? Because that's the goal of contrastive learning. Mathematically, you can see this, when we train a clip, we have to come up with something called a loss function. So any neural network, when we train, we need to have a loss function. The loss function is basically a function of the mistakes the neural network is making. All right. So if the neural network, and this loss function is used to change the parameters of the neural network. You can think of a neural network, any neural network, as a black box with different knobs, right? And these knobs there are millions of these knobs. When the settings of these knobs they are good, they are in a good setting, then the neural network produces the right result most of the time, right? If they are not in the right setting, it means that it's not going to produce the right answer to whatever your input is. So the goal of training the neural network is to find the right settings for these knobs. And the way we do it is we take a bunch of images, we pass it through the neural network, see the output, and because we know during training, we know what the expected output should be, we can find the error it is making, what is the mistake the neural network is making. And then we go back and change the weights or the parameters of the neural networks. These knob settings we change in a principled way so that the next time it sees these images, it is doing a better job, right? So the loss function basically is a function of the mistake it is making. And as I had mentioned,
Got a quick question from
Yeah.
the peanut gallery here,
All
which
right.
I missed a moment ago. Says using the same vector size for the image and text, could this be wasting extra storage and compute for the text, which appears to be smaller than the image vector?
That's a very good question. The thing is that the reason, first of all, 512 length vector, it's relatively small, right? It is just 512 numbers. Think about an image, it can contain so many more numbers, right? I mean, even a small 100 by 100 image and 3 channels, that would have 30,000 numbers, right? So the main goal of this vector space, right, is to be invariant to what the input is, whether you are giving a text as input or whether you are giving an image as input, you should receive the same vector, right? So it becomes invariant to the modality. You could also add a speech modality to it, right? Where you say that if the same concept, let's say the man wearing a mask, the text man wearing a mask is the same concept as the picture of a man wearing a mask, and both of them should result in similar vectors, or at least vectors that are aligned pointing in the same direction. Now you could also add another modality like speech, and you would say that, oh, man wearing a vector, not wearing a vector, man wearing a mask, and that speech that could be encoded into the same vector space, right? The reason we do this conversion from all these different modalities to vector spaces is that now we have, once you have everything embedded in the same space, you could do linear algebra on it, right? You could minimize things in it. You could use all the different algorithms that the people in linear algebra community have been developing since ages. And that's so basically you can do math on different kinds of modalities, right? That is why they need to be in the same vector space. So think about the vector space, the embedding space, as a conceptual space. It doesn't matter which modality is producing this vector, they should all be the same, right? It's basically encoding the concept. It doesn't matter where the concept came from. It could have come from an image, it could have come from text, it could have come from speech. They are all encoding the concept into a vector. Does that make sense?
Yes, thanks for the great explanation there.
All right. So again, I'm not going to go into, it looks very complicated, this loss function, but it is not. Basically, it is the same idea that I had explained. For every image, you try to minimize the distance between the image and its own caption and maximize the distance between the image and all other captions, right? So here you can see that in the numerator, we are trying to forget about the exponent part, look at the similarity, right? So the numerator is big or large when we have the image and its own caption. So you can see that this is I, and here we have I and J. So it's being normalized by all other image caption pairs, right? So this number is large when for the image caption pair, which is the same image caption pair, right? And it is small when it is different image caption pairs. And you can see that negative here make sure that the whole thing is small, right? When you have the right image caption pairs. So this is being minimized, right? This loss is being minimized for us to go train the neural network or the vision language model. Okay, so that's the loss function. It's the most important thing to understand. And after that, let's look at the architecture and the training method, right? again, I said that there are two pieces. One is the vision encoder, the other is a text encoder. The vision encoder has two options. One is a ResNet 50 based convolutional neural network backbone, and the other one is a vision transformer, right? So those are the two models that they trained. And the output vector is 512, as I had mentioned. The text encoder is a 12-layer transformer. It has about 63 million parameters with 8 attention heads. Again, don't worry about what the details are. We can, you can go and read up on those later on. But it is very similar to a GPT architecture. The most important thing is that it also produces a vector of size 512. So if you want to take one thing from this slide, you have to remember that the vision encoder basically takes an image of any size and it produces an output vector of size 512, of length 512. The text encoder similarly takes any text, a text of any length, and it outputs a vector of size 512. And if this is trained properly using the loss function that we just discussed, then these two vectors would be aligned. They would not be in the same space, right? But they would be aligned. They would be pointing in the same direction, right? And if you normalize them by their length, right, the length of the vector, then they would be at the same space, right? So basically, the training process, the idea of training is so that these image caption pairs get aligned. Okay. So some details about the training. First of all, this is trained from scratch. They did not use any pre-trained weights from ImageNet or any NLP model. And the reason is that they are working with such large data set, right, of 400 million images, that they don't need to start with ImageNet or any other weights, because sizes of those are smaller, right? And the other thing is that they used very large mini batches. They used mini batches of size 32,768. So a mini batch, when you're training a neural network, you do not take all the data, right? You cannot take 400 million images and put it on the GPU. There is not enough space. So you have to select a few images at a time and then put it on the GPU, calculate the error. Using that error, you calculate how the model weights should be changed. And then this thing continues over the entire data set, right? You select a few images at a time. But if you have ever trained a convolutional neural network, you would know the batch sizes are nowhere comparable to this one. Usually the batch sizes are 32, 64, maybe 128, right? That's the typical batch size, that those many images are picked from the training set and used to train one step. Okay. Now, the reason they need such big batch sizes is because think about it, right? When you have two images, there could be, when you select a collection of images and you have a image of a cat and the caption is, let's say, a cat walking, you could find another image in the collection which also is an image of a cat, and the caption could be a cat walking. If you have a large batch size, this kind of mistake, right? This kind of mistake is contributing only a small amount to the loss, right? But so because you remember, the way we train the model, the way the loss function works is that given an image, it is trying to maximize the distance between the similarity between the image and its own caption. For all of the captions in this mini batch, it is going to try to minimize the distance. And we don't know a priori whether these things are similar to each other or not. And so having a large batch size ensures that even if we are making a mistake, that mistake doesn't contribute a lot to the final loss function. And then the choice of contrastive loss, right? It is also very important. There are other things that people could have done, right? The authors of this paper, they could have trained the neural network using a slightly different loss function. For example, they could have used they could have used the image to predict the caption, and then the predicted caption and the actual caption, they could have taken the difference between those, and that could be the error, right? And that kind of generative approach, it was very expensive, and that is why they did not choose it. This alignment was much faster, and that is why they chose it. Okay, so that is a little bit about the contrastive loss choice. Now, before we leave this set of slides, I want to mention that there are several limitations of this. First of all, clip kind of architecture, it is very good at high level things, right? But it doesn't do fine-grained image classification. So it cannot tell the difference between two different varieties of dog, for example, right? It can say that this is a dog, right, and this is a cat, but it won't be able to align when there are two different breeds of dog, because there is not enough examples. It also doesn't do very good on out of distribution generalization. For example, it works very poorly when you show it handwritten digits from MNIST. And if you have trained any neural network, right, if you are familiar with neural networks at all, convolutional neural networks, you know that MNIST is like the hello world problem of computer vision. So you basically can easily train an MNIST on MNIST dataset, which produces more than 99% accuracy, but this vision language model will not do it. You can actually fine tune the model to make it work, but out of the box, it's actually not going to do very good on MNIST, right? And it is also very sensitive to the phrasing of the prompt. Another very important thing is that
it's like we lost your screen share there, Doc.
Oh, you did? Let me.
While we take a look at that, maybe now is a good time for me to do a quick ad read from today's episode sponsor, Big Vision. I'm going to go ahead and do that here. Let me bring myself back. Yeah, hey there, everybody. So, gonna full screen fill. Yeah, so OpenCV Live. This episode is brought to you by Big Vision. Every company needs a big vision, and they're a consultancy run by our very own Dr. Satya Malik. I'm going to share the screen, and we'll take a look at their website here real quick. Okay.
And while Phil is coming up with the website, I just want to mention that sponsorships are available. We are happy to take sponsorships from any company. It is basically, we have an introductory price of $250 only per episode, but you have to buy it for 4 episodes. So if you or your company wants to sponsor an episode, you can simply buy this package, send us an email at phil@opencv.org, and we'll take care of it.
That's right. Today's episode is brought to you by Big Vision. Every business needs a Big Vision. Consulting services in AI, computer vision, and deep learning. You can see some of the major organizations that depend on Big Vision for their expertise, such as TechCrunch, the BBC, Wall Street Journal, Time Magazine, the Register, lots of journalistic organizations, including the Oprah magazine, which was a surprise to me.
They have carried articles about Big Vision.
That's right. Expert AI consultancy services for real-life business problems. Big Vision is the perfect partner for businesses looking to hire passionate, world-class AI researchers and engineers. As we said, they've been featured in the Wall Street Journal, Time Magazine, the Oprah Magazine, amongst many others. They build specific AI-driven solutions, create intelligent processes, and establish best practices to significantly reduce human effort and enable faster decision-making for your business. You can find out more by going to bigvision.ai. Get in touch with them, send them an email, see how Big Vision can help your business have a big vision.
Thank you, Phil.
Yes, no problem. Yes, and of course we are available. We're selling our souls for rock and roll for the price of just $250 per episode. You can buy a pack of 4 to advertise to the over 117,000 subscribers on OpenCV's YouTube channel by sending an email to me. That's phil@opencv.org. Hit me up.
All right. So we were. Can you see my screen now?
That's right. I'm bringing it back up. There we go.
All right. So you have to be very careful about the biases that these models have in them. It absorbs all the societal biases. You can imagine that 400 million image caption pairs, they have actually not verified each one of them, whether that's correct or not. So you could have a lot of, there can be a lot of problems in this kind of model. So you have to do a lot of testing before you release a product that uses a model like Clip. And there are also ethical concerns, right? It can be misused for surveillance, for face recognition, these kinds of things. And you have to be careful that you do not do this. There was an example where they showed that, if you look at a person's face and try to guess whether they're a criminal or not, you can use Clip to do that. But it's a really bad idea because the face doesn't have any information whether they are a criminal or not. But Clip latches on to the age of the person. So Clip, if the person is younger, it would say that, oh, this person is most likely to be a criminal. So if you have only two classes, right, you're building a classifier using Clip, which we will see how to build a classifier, and you had just criminal and non-criminal, right? You did not have a category like child. In that case, it is going to classify everything into one of these two categories, and it will classify or misclassify kids or younger people as criminals, right? So you have to be very
And
careful.
because also, the way that society sort of classifies what is and isn't criminal, the businessman who steals millions of dollars in wage theft from his employees, we don't tend to call that guy a criminal. We call him a titan of industry. And so it's not quite the same. Basically, when you use AI for stuff, in a lot of ways, you just end up redoing phrenology, which is the 1800 pseudoscience where they thought they could tell whether someone was like a criminal or intelligent or not by the shape of their skull, which is obviously just it's just another way to implement racism.
Right. Yeah, I have a whole thing about these IQ tests. Also, they are.
Yeah, thanks a lot, Stanford.
No, so okay, that's a separate. I have we are limited on time. Otherwise, my family does very well on IQ tests, but I hate it because I know that it is biased towards a certain kind of people.
Yes.
So let's move on to some notebooks. Right now, for people who may be wondering how do they get access to all this material. Actually, these slides, this material is from our free VLM course. We have already launched this. You can go to OpenCV University right now, and you can get access to this course. And this is basically some of the material from the course, not all of the material. So you can get these notebooks, these slides, everything, this video, you can go and watch it there. So let's go with the first notebook, right? And in this notebook, we are going to learn about embeddings. You remember that we have two different pieces in Clip. One is a vision encoder, the other is a text encoder. The vision encoder takes in an image and encodes it into a vector of size 512. And the text encoder does the same thing for a text string. And these vectors are called embeddings, right? And we'll see some interesting facts about these things, right? So if you're running these notebooks, make sure that if you can, this runtime is basically a GPU. You may, even if you do not have a paid version, you may have access to one of these GPUs, right? T4 or L4. So use a GPU. It will save you time. Okay, so to start this notebook, we are going to use the implementation of Clip inside the transformer package, right? Transformers, it's a very useful package by Hugging Face. In fact, this is the package that literally made Hugging Face the company it is today, because when the transformer architecture came out, it was implemented in TensorFlow, and they saw an opportunity. They created the PyTorch version of transformer and made it really nice and easy to use using this transformer package. And a lot of people started using it, and this became the standard. So from the transformer package, we are going to import clip tokenizer. I'm going to talk about tokenizer in just a bit. Don't worry about it. But this is basically used given a text string, it basically creates a vector of numbers from that text. We'll come to it. We'll also import the preprocessor or processor. The processor basically normalizes the text as well as images, and we'll see how it is done as well, right? And then finally, we are importing the clip model. And the transformer package makes it so easy that you can simply give it the name of the model, and it will download the model for you, and it will also download the processor for you, which will help you process the image, etc. And very easy. It makes it very easy. Then we are importing torch. We are getting this functional, for cosine transform, we are getting this functional f. And then we have standard imports like NumPy, Matplotlib. Seaborn is basically a library for creating statistical visualization. We'll see it for, we'll create a heat map using it. And the others are pretty standard, right? PIL for importing image, for getting images. We have requests for downloading images. And then, IO basically helps us read binary data as a file-like object. Okay, so we start by this model, right? The model name is OpenAI /clip-vit-base-patch32. Now, this is the vision transformer version of the clip model that we had mentioned. And we are going to, sometimes you will see these, the models have names like base versus instruct. So base model means that it is the raw model. When you see the word instruct, it means that it is a chat-like model. So this is not a chat-like model. It is basically a one-shot model where you give the image or image caption pair, you get the embeddings out of it. Okay. So to get the model, you basically do clip.model from pre-trained and give it the model name, and out comes the model. So easy. It does all the downloading for you. Don't have to worry about anything, right? Now, next, we are going to tokenize a text string. Okay, so again, the transformer package makes it so easy for us to use the tokenizer, and I'm going to explain what tokenizer is in just a bit. But all you have to do is pass in the model name, and it gives you the tokenizer. Okay. And then we have these text strings. There are 4 pieces of strings, right? A donut, a cookie, an airplane, a cat. And we are trying to find, using this text string, we are going to tokenize it first, and we'll see what this tokenizer actually does, right? So the tokenizer, we have to pass in the text, right? The text is, these are the 4 strings that we are going to pass it. We are going to say that padding is true, which means that if these texts were of different lengths, they will all be normalized so that it will pad the final result so that all the vectors it produces, it is of the same size. And then we say that the return tensors, we set it to PyTorch, right? Because the same package can also be used in TensorFlow and other packages. Here we are explicitly saying that we are going to use PyTorch, and so return it in the PyTorch format. Okay. So from the text string, we get the inputs. To see what is in the inputs, we are going to just do a shape first, right? We'll get the input IDs, and we are going to look at the shape, and then we are going to print out the input IDs themselves. So if you look at this shape, we got a shape of 4x4. So one of the 4s is for, we have 4 entities here, right? We have 4 text strings, and the other 4 is the output vector has a length of 4. Okay. So you can see that each vector has 2 components. Now is a good time to explain what a tokenizer is. Given a text string, it converts the text string into a vector of numbers. And you can roughly think about these numbers as a token as a word. It is not exactly a word, but you can roughly think about think of it as a word. Okay, for all practical purposes, you can think about it as a word, and you'll be fine. So you can see that the 4 words, right? We had these donut, a cookie, an airplane, and a cat. It has been tokenized into this vector. So all of these vectors, you can see there is a starting number, right? 49406, and ending number 49407. This basically represents the start of any string and the end of any string. And then you can see that the word A, right? Or it's probably A followed by the space. This thing is 1 token, right? And that is encoded as the number 320. Okay. And an is encoded as the number 550. Just to give you an idea, let's say I make it A airplane, right? If you look at the token, they are all 320. Okay. And these basically represent airplane, donut, cookie, etc. Now the token, it's not an embedding, right? This is not of length 512. This is not an embedding because it is basically taking the string and dividing it into words, right, or tokens. And every token has a number associated with it, but it is not a semantically important vector, which means that it doesn't. If you have two concepts, right? Let's say a donut and a cookie, they are similar concepts because they are both food items. They are sweet, right? So, but if you do the tokenization, right, it doesn't matter, right? It is these two vectors are not going to be aligned, or they will not be similar in any respect. It is just a collection of numbers. So once we have tokenized, we need to actually find the embedding. And to do that, we basically do torch.nograd. So whenever you want to use PyTorch and you want to use the model for inference, which means that you're not using it for training, we have to use this option, nograd, so that it doesn't calculate the gradients. This makes sure that things are running faster, right? So with this thing set, we find the text embedding. To find the text embedding, we basically pass in the tokenized, the output of the tokenizer, and we just do get text features, model.get text features. So easy. And we just pass in these inputs that we had created, we get the text embedding. Now, if you look at the text embedding, if you look at the shape of the text embedding, it is 4 by 512. Okay. So to process text, we had to basically tokenize it, right? So any text string, this model doesn't consume it directly, it consumes tokens. So we have to first tokenize all the strings, and then we basically pass all these tokenized strings into the model, and it gives us the embedding, right? That is the purpose of the model. Give it a string in tokenized format, and it will give you an embedding, okay? So we get 4 vectors of size 512, and that's what it does, okay? We have already talked about what a cosine transform is, or cosine similarity is. We can find, PyTorch has cosine similarity built into it, and we can use it to calculate cosine similarity between 2 vectors. Okay. So here we are passing in the cosine similarity. We are using the functional to calculate the cosine similarity. You can see that we are passing the text embedding twice, so that it finds pairwise distances, right? Pairwise similarity between the text. And then we are basically using some plotting technique, right, to plot it as a heat map. So let me show you what the final result is. When we plot this thing, we will get this cosine similarity matrix. If you look at the x-axis, on the x-axis, we have text embedding. On the y-axis, we also have text embedding. So we are basically comparing the embeddings pairwise of these 4 text strings, right? A donut, a cookie, an airplane, and a cat. And as you can expect, that the cosine similarity between a text string and itself is 1, right? It is the same string. So the cosine similarity is 1. But if you look at the distance between a donut and a cookie, right? So this 0.89, it is basically the similarity between a donut and a cookie. And you can see that it is 0.89, which is higher than a donut and an airplane, right? So you can see that similar concepts, they are placed together when you embed in this text embeddings, right? So donut and cookies, they are similar concepts. They are both food items which are sweet. So they are kind of in the similar space, right? That is why the similarity between them is higher than the similarity between a donut and an airplane. Okay, and we can do the exact same thing for images also. Now, here we are basically writing a small function to plot a bunch of images that we download, and then we get a processor for the model, right? So this model can take any image, but it actually doesn't take any image size, right? What happens is we need to pre-process the image. So when you take any image, first of all, you need to reduce it to size 224 by 224. And the way you do it is that you resize the image such that the smaller size is of size 224 and the longer size you center crop it, right? So you center crop it, and now you have an image which is 224 by 224. You also have to do subtract the mean of this image. Subtracting the mean from an image makes all the images brightness invariant, right? So we are basically helping the model by normalizing the image. We subtract the mean of the image, it becomes normalized for brightness. Similarly, we divide it by the variance of the pixel values, and it becomes invariant to contrast, right? So there are these pre-processing things that you need to do before the image is ready for the model, right? And fortunately, all these things are implemented in the transformer package, and we do not have to do any of this, right? So we basically get the processor, and we just pass in the model name, and it gives us the right processor. And then we basically we download all these images, and we are showing it, right? Initially, we are just downloading all these images, and we are displaying it. So this is an image of a donut, a cookie, an airplane, and a cat, okay? And to calculate the embedding, first we get the image in the right input format. So we use the processor. So the image that we start with, it could be generic, it could be any size. And then when you pass it through the processor, it becomes of a specific size, 224 by 224, with the mean subtracted and normalized by the variance. Once you do that, we are ready to pass in these images and calculate the image embeddings, right? And we do the same thing. We make sure that the model doesn't calculate the gradient, right? And we so that it is faster. We get the image embeddings, and then we print the shape of the image embedding. And as you can expect, the shape of the image embedding is 4 by 512. So given an image, the model produces an output which is of size 512, okay? So, and again, we are doing the same thing that we did for, once we have the vector, we can actually create the cosine similarity matrix. And you can see this is the new cosine similarity matrix, right? And this is based on images. The previous one was based on text. But the interesting thing is that you can see here that this is image embedding, and this is also image embedding. So the dominant one, the diagonal, is all one, because an image of a donut has the same embedding as the image of a donut. No surprises there. But here it's interesting, right? You can see that, again, the donut and the cookie, they are close together, right? This is 0.69, which means that the idea of a donut is close to the idea of a cookie, even though the modality was an image, right? The information came from an image, but when we found the embedding and we tried to do the similarity, it kind of has similar structure. So this heat map has a very similar structure to this heat map, which was produced using text, right? So now you can see where we are going with this, right? We first took the text, we embedded it, we took the image, and then we embedded it. Now let's find the cosine similarity between an image and its and the caption or the text. Okay, and we can do the same thing, calculate text image similarity, and you can see on the x-axis we have text embeddings, on the y-axis we have image embeddings. The diagonal is still dominant, right? The diagonal is still dominant. It is not as pretty as before, right? It is not one, obviously, because one of them is a text embedding and the other one is an image embedding. But you can see that the diagonal is still dominant, which means that the image of a donut aligns with the text donut, right? This is the highest, right? The red means it is a high value, and it is higher than all of these other values. All right. So now it gives you a sense, right, that no matter whether you use an image or a text, it is creating an embedding for us, which is which you can actually use for image classification, as we will see later on. Okay, so from this notebook, if you understood these concepts, all right, these are the concepts that you absolutely need to understand. First of all, you need to understand what is tokenization. And just to recap, tokenization is basically a vector representation of any text, right? A token is roughly a word. It is not exactly a word. It is roughly a word. You can think about it. And it's a numerical representation of roughly a word. Okay, that's what a token is. But these neural networks, they don't take raw text, right? So we have to tokenize them. They use tokenized text as input. So once we have tokenized it, they can be served as an input, and we can get the image or the text embedding. Similarly, for images, we can start with an image. We can apply the processor to it so that it processes the image into the right format, and then we pass it through the model, and we can get an image embedding. Once you get a text embedding and an image embedding, you can calculate the cosine similarity between them, because these are just vectors. You can calculate the cosine similarity between any two vectors of the same size. And if you understood cosine similarity, you will know, that these images and text, they get aligned when you're using CLIP as the model. Okay. So any other questions? I'll go to the next notebook and show you how we can use this for zero-shot classification. But if you have any questions about this notebook, I can answer it right now. We've
got quite a few questions here. Let me go ahead and bring some up on the screen here. As a reminder, folks, you can support, one of the ways you can support OpenCV is by becoming a member on the YouTube channel. You can go to OpenCV's official YouTube channel. It's youtube.com/@OpenCVofficial or opencv.org/live. Find out how you can support OpenCV for just a couple bucks a month and get some YouTube exclusive perks. Let's grab us some questions here. Bring up Satya. Okay, so we've got, let's bring up Avik here. How critical is the scale and diversity of the data set for achieving robust representations, and what happens when using smaller or noisy/weakly paired data?
Yeah, so the scale is very important, right? 400 million images, that's the scale you need to make these things work. Noisy is fine. The better, of course, if you have, every data is manually verified, then it would be really good, but that's not the case. These are scraped from the internet, so the data is very noisy and it works fine, right? But the scale is very important.
Yeah, thanks for that. We've got a couple more here. I'm going to bring up one from LinkedIn here. Vamsi asks, how can we decide the type of embedding space we require as per the task or requirement?
So when you're using CLIP, you don't have to decide anything. It has been decided for you, right? It is basically, it embeds text and image in the same space of 512 dimensions. And in most cases, it's very, very unlikely, unless you're working at a very large company which is doing fundamental research, that you would actually change this space, right? So basically, you need to find problems that CLIP can solve, and all it's doing is no matter which modality you use, whether you use an image or a text, it is creating an embedding for you, and then you can look at the cosine distance between the two vectors and say whether they are similar or not, right? So if your problem is in this format, right, then you can do it. You can also fine tune CLIP for your own problem. For example, I gave you the example of MNIST. It doesn't do well out of the box for MNIST dataset, but you can actually fine tune your model with MNIST. You can give it enough image caption pairs, and it will produce the right answer, right? So yeah, so you basically don't decide what embedding space would be needed. CLIP does it for you. It has already been trained for this task, and you find the task, right? For many tasks where you want to do alignment of image and text, it works great out of the box. And in the worst case, you have to do some fine tuning.
All right, thank you again for that. We've got one more question here from YouTube. Let me pull it up on screen here. Ask, what's the difference, pros and cons, of using Transformer versus using Ollama server with a vision model?
So I have actually not used Ollama server plus vision model. So, but my guess is that the question is basically using vision language model versus using a language model plus vision, right? So plus another vision model like a convolutional neural network, etc. So a VLM is very useful because it jointly learns the idea of an image and text. When you use a language model, independent and a separate vision model, it can be useful in some cases, right? And maybe it is the right approach in certain cases. But in most cases, you're better off using a vision language model directly. I'll give you an example. Let's say you want to identify an object, let's say a shampoo bottle, right? You want to identify it without having any training data, right? One way to do it is that you use a vision model to build an object detector, a class agnostic object detector, and you basically find all the bottles which are like shampoo bottles, right? Then you do an OCR on it, right? You find all the text in it, and then you pass it to a large language model to ask it, right? I found this text on a shampoo bottle, right? Or on a bottle. What shampoo is it, right? And it will give you an answer. So this approach will work, but you can also use a vision language model directly and extract this information, right? Because there are advanced vision language models today. For example, Quen 2.5 VL would do the bounding boxes for you, right? You can ask it to extract bounding boxes and tell me what's in the bounding box, and it will do that for you in one shot, right? So I hope that answers your question.
Thanks for that, Doc. And for the folks asking out there, yes, you can find every episode, past and present, of OpenCV Live on the official OpenCV webpage. It's opencv.org/live. I think let's take a moment here while we're paused to do our giveaway, because I know some folks have a hard stop, and then we'll continue on with the presentation, shall we? So I'll go ahead and bring myself back on here. Show Phil's camera. Okay. Yeah. So, oh wow, that's not what I meant to do. But hey, everybody, you can see backstage there a little bit. I hope you enjoy. This is the inside baseball. But yeah, let me go ahead and bring us back to, yes, indeed. So, folks, if you're just joining us for the first time, or if you need a reminder, one of the things we do on this show every single episode is give away something to you in the audience. I am about to ask a trivia question that I have made up based on today's presentation, and the very first person to answer that trivia question, wherever you're watching, whether it's on Zoom, YouTube, LinkedIn, Twitch, TikTok, anywhere, the first person to answer correctly in the chat will win the OpenCV University course of their choosing, and then we'll get on with the presentation and more of your questions and comments. So get ready to answer. And if you have won in the last couple of months, please do not answer and give someone else a chance to win. I'm going to go ahead and post the question here. Today's trivia question is, in what year and by what company was CLIP originally released? That's 2 answers, the year and the name of the company. Answer today to win the free OpenCV University course of your choosing. Put it in the chat wherever you're watching. And wow, we've got Hokey Smokes, Campbell in Zoom. Knocked it out of the park very, very quickly there before I even got the words out of my mouth. The answer we were looking for is 2021, and the company is OpenAI. The answers we were looking for is 2021 OpenAI. Congratulations, Campbell H. in Zoom. Please send exactly 1 email to me. That's phil@opencv.org. With the OpenCV University course that you would like. You can see what courses are on offer by going to OpenCV University's webpage, by scanning the QR code on your screen right now. See what courses we got. Even if you didn't win today's trivia challenge, invest in yourself, invest in your career, level up your understanding of the most consequential technologies of the day, and maybe get paid more at your current job, get a better job, or just do it because you're interested. Go to opencv.org/university. We've got some free courses on there, including much of the materials you've seen here today with the Vision Language Model Starter course there. Also, OpenCV is a nonprofit organization that puts out free software, and as such, we depend on donations to survive. You can see how you can support and help OpenCV by going to opencv.org/support. I'd like to quickly thank OpenCV's sponsors right now by sharing my screen. I'm going to share a window. Yes, indeed. And we're going to go to opencv.org. Oof, there we go. Yes. Turn off this QR code here. OpenCV is the world's biggest computer vision library. Since June of 2000, we've been doing it. We're still doing it, and we owe a lot of the fact that we're still doing it to these wonderful companies, our members and partners that support OpenCV on an ongoing basis. If your company uses OpenCV heavily, please consider becoming an OpenCV member. OpenCV has a robust membership program for companies of all sizes. You can find out all about it by going to opencv.org/support. You can donate to OpenCV as an individual via PayPal, via Stripe. You can also, depending on where you work, occasionally your company may do matching donations. If you work at a large company, they might take, say, for example, if you donate $500, they may make that $500 $1,000. So talk to your boss. If you use a system called Benevity, you can use that matching donation stuff. Also, in some cases, your company may match your time. If you do some work, maybe submit a pull request or fix some bugs on OpenCV's codebase, your organization may match that time you spent in money. So ask your boss about it. Send us an email about it. Like I said, I'm an easy guy to get at, phil@opencv.org. I'd be happy to talk with you about that. If your company uses OpenCV heavily, consider becoming a member. We've got 3 tiers, bronze, silver, and gold, for companies of all shapes and sizes. You get a lot of benefits for doing so, such as appearances on this very program. OpenCV Live goes out to 117,000 subscribers. We had a peak of 80 live viewers here today, and we really appreciate everybody watching here. Also, the ability to put stuff in the OpenCV newsletter, which goes out to 350,000 people every week. And of course, the good feeling of knowing that you're supporting open source software and keeping it going. You can also buy stuff on OpenCV's official shop, opencv.myspreadshop.com. Let's take a look there. 20% off everything right now, including the iconic import CV2 command on hats, shirts, hoodies, etc., as well as the OpenCV logo and the I Love OpenCV design in English, simplified Chinese, and in Espanol. You can also sponsor OpenCV on GitHub by going to github.com/sponsors/OpenCV. We've got 12 sponsors right there. I'll give them their 5 seconds of fame right now. Shout out to LivePeer. Shout out to iPop. Shout out to DJ Greenwood, Ruddis Laboratories, Tala Hussein, the homies at RoboFlow, Alexander Ismailov, Comet ML, Jonas Heinle, Nick Libertini, Blue Jay, and Jesus Armando Anaya. Thanks so much for your support. You can be as cool as these people by going to github.com/sponsors/OpenCV and cutting us a monthly donation, or even just one time, and I'll read your name on the show here. That is about it for right now. I will take off my screen share and we can get on with it, as they say. What do we got next, Doc?
Well, we'll talk about zero-shot image classification using CLIP. This is one of the applications, very common applications of
All right, let
CLIP.
me bring up your screen share again, and here we go.
All right. So this notebook is about zero-shot image classification. For people who are not familiar with image classification, I'll just give you an overview first. In image classification, you have a neural network, and the input is an image. The output is a class label. So it outputs the probability of things being a certain class, right? So for example, here the input is an image of a dog. This neural network outputs this vector, which basically gives you the probability of different classes. The cat has probability 0.08, dog 0.91, and other, right? So it has 3 different classes it can classify this image into. Now, if you want to train a neural network, right, a convolutional neural network that does this kind of thing, you would have to get, let's say 1,000 images of cats, 1,000 images of dogs, and 1,000 images of other classes, right, random other classes, and you put that, and you train the model, and you will be able to build a classifier like this, right? Now, suppose somebody comes in and says that, oh, I forgot I got a new pet elephant, right? I want to add my pet elephant, right? I want an elephant detector as well. So now what you do is you go back, you collect 1,000 images of elephants, and then you retrain the model. You have cats, dogs, elephants, and other. And then, it takes a few days. You had to actually go and collect all the data for elephants, and you had to retrain the model for the neural network, right? So that is not zero shot, right? That is basically training from scratch the entire model. Zero shot would be that you change one line of code without doing any training. You're able to add the elephant class, right? So let's see how it is done, right? Now, again, we have some standard imports. We have gone over them, so we are not going over this. We get the model just like before. We get the CLIP model from from OpenAI /clip-vit-base-patch32, and then we load this CLIP model, right? Just to give you an idea, basically we load the processor. In the previous notebook, I took you through the steps of tokenization and then doing the text embedding, but it's actually not required. I just wanted to show you what tokenization means. You can actually use the processor directly, and it will give you the embedding starting from the text. It basically does the tokenization internally, right? So just to get you an idea what this CLIP processor does, right? First of all, like I said, that it does this 224 by 224, and then center crop. It does all these resizing, rescaling, etc. It subtracts the mean, different color channels mean you have seen, and then it divides it by the standard deviation, and all these things, right? It does all this thing for you. And the same thing it does, the tokenizer is also embedded in the processor. In the previous notebook, I showed it as a separate thing, but you don't have to do it as a separate thing. I just wanted to explain what's going on inside the tokenizer. You can give the processor, you can use the processor to do the tokenization as well as the embedding for you, the tokenization for you without doing it explicitly, right? So the tokenizer is also embedded in the processor. So in this notebook, you will see I'm a little short on time. I have a hard stop at 10:30 my time, which is 15 minutes from now. So I'm going to run over this notebook faster. But you can see, this notebook will explains all the different image processing as well as text processing steps that the processor does for you, right? So that's what we are doing here. We are getting the processor, and we just need to supply the name of the model. Once we get the processor, right, I'm going to load this image, right? And this code is simply loading this image and displaying it. As you can see, that this is image of a cat or cats, okay? Now we have three classes. In this classifier, we are going to have three classes: cat, dog, and rabbit, right? And that is, we will pass this text through the processor and get the input, and then we'll embed the text. We'll also embed this image, and now you can imagine what we are going to do next, right? We can look at the image embedding, compare it with the text embedding, which any one of this, the one that gives the highest similarity is the class label, right? So here we get the inputs. Now the processor can take both text and the image in one shot, right? So in the previous notebook, we did not do that, but you can see here that we are using the text, the processor for passing in the text as well as the images, and it will give us all the inputs, right? All the inputs are in here, and we are just saying that, okay, return tensor, this is of PyTorch type, and the padding, as we know, the text needs to be padded to the same length. So once we have done that, you can see, we can do the same thing. We get the input, and you can look at the shape of the input, and this is the same thing. You will remember that it has done the tokenization for us. 4946 is the start of the string. This is the end of the string, and this is basically cat, dog, rabbit. Okay. It also does. I'll skip over this attention mask, but okay, I'll say it. Let's say you had parts. Let's say the strings were of different lengths. Then this attention mask would tell which part to focus on, right? So it would be zeros in places where there was just padding, right? So basically, it says that ignore all these extra tokens. They are just used to make the size of the strings the same. But here we are only, the size of these strings are the same, and that is why you see that the mask is 111 all throughout. Okay. You can also look at the pixel values, right? After this thing has done the pre-processing, you can see the pixel values, and as you would expect, the size is 224 by 224 by 3. 3 is the number of channels, and 1 is the one here is basically the batch size. You could actually in PyTorch, usually you can process multiple images in the same as a batch. That is the common way of doing. So if you have an image, you have to convert it into a tensor, right? So that is why you see this extra dimension. If you look at the pixel values, they are no longer between 0 and 255. They have first been normalized from 0 to 1, and then you subtract the mean and divide it by the standard deviation, and that is why you see some negative numbers here also, right? You're subtracting the mean, dividing by the standard deviation. So, and then now, we'll do a forward pass. We will use the model, pass the inputs, and get the output. The output will contain many different things, right? First of all, it will contain the text embeds. It will also contain the image embedding, and then it will contain the logits per image, right? So this is the output. Logit per image for all the images, right? This calculates the similarity score between the image and all the different captions, all the different text for every image. In this case, we are just passing in a single image, so it will be a single image, right? So you can see we are doing this outputs.textembed.shape, which is as expected. There are 3 texts. So we have 3 by 512. We have 1 image. That is why the image embed is 1 by 512. Then we look at the shape of the logit per image. We have 1 image and 3 text, and it is going to find the similarity between the 1 image and the 3 pieces of text. And you will see this logits, right? And even looking at this, you can say that the first one is greater than the others, right? But these are not probabilities, right? They don't add up to 1. So we have to basically transform this, right? We have to transform these numbers into probabilities. And that is done using softmax, right? Now, the way to think about the software, you can look at this. This is how softmax is calculated. You can take any vector and apply softmax to it, and it will return probabilities from these from this vector. Now, to understand softmax, think about hardmax, right? If we had a vector like this and we wanted to find another vector where the maximum of the vector is 1 and all other numbers are 0, in that case, that would be called a hardmax. And a hardmax would basically say that, oh, there is 1 here, 0, 0, right? A hardmax function would take in this tensor and return another tensor, which is 1, 0, 0. Okay? A softmax is a softer version of it, right? It basically returns something which is, it still gives a lot of weight to the maximum, but it distributes some probability in other classes also. So you can see that once we take this, these numbers were looking very similar to each other, but when you do a softmax on it, you will see that the probability of cat is 0.96, the probability of dog is much smaller, and the probability of rabbit is even smaller, right? So now you can see that we did not train this model, right? We did not train this model on cat, dog, or rabbit. And yet we got an image classifier out of the box, right? So now you can imagine, let's say you want to add another class called elephant, right? All you have to do is go to this spot where we had that, go to this spot, add a class, right? Like elephant, and it will be able to, that's it. It's 0 shot, right? You just did this, you run the code again, and you will be able to classify an image of an elephant correctly, right? So that's what 0 shot image classification is using CLIP. And you can see that, it's not that there's no magic going on. It is just that it has been trained on such a large data set that all these classes, it has an understanding of all these classes, and we can get to these classes using text, because all the information about the images, all the different elephants is already embedded in the model. And we know that we can poke the model in 2 different ways. We can give it an image, it will give us an embedding. We can give it text, and it will give us an embedding. All we have to do is find the similarity between them to see whether the text and the image, they represent the same concept or not, right? So so that's 0 shot image classification using CLIP. And I can take some questions right now, but I have a hard stop in about 5 minutes.
Okay, let me go ahead and take off your screen share here.
One other thing that these notebooks, everything, it's available on OpenCV University. You can go to OpenCV University, sign up for the VLM bootcamp, and you will find not only these notebooks, there are extra notebooks that are part of our free VLM course. And in a month or so, we are also going to launch a Kickstarter campaign for a full-blown vision language model course, which will be 30-40 hours of material would be there. So that would be a paid course, but the one that we have right now, it's a free course. It's a much shorter course. You can finish it in about 3 hours or so, and you will learn about CLIP. You will also learn about Quen, which is another vision language model, very powerful. It's a conversational vision language model as well. It's not a one-shot thing. So you'll find a lot of value from this free course alone.
Yes, indeed. You can go to opencv.org/university to see what courses we got there and get those free courses as well. They're a little bit shorter, not quite as in depth, but they are free and they're pretty damn good. Let's take a look at some questions here from the Peanut Gallery. We've got quite a few over on Zoom. I think we got to most of the answers to those, though. So let's take a look back at YouTube. Interesting. I have this one's out of my wheelhouse, but possibly in yours from Dronzer. Trying to fine-tune clip on a KITTI dataset 7.5K image question pair to experiment with fusion strategies, but the model is getting overfit. Is it because of the scale?
Yeah, so the Kitty dataset is not useful. I mean, I'm assuming that
Drag their asses,
this is part
King. All
of that.
right.
This is part of the 400 million image already, right? Any free thing that was available, they would have used it, and I'm guessing that it's not useful just because it's already part. So the reason to fine tune, right? There's only one reason to fine tune, is when you want to associate a concept with something new. For example, I could fine tune clip with my pictures, and then I would have a word, Satya Malik, right? That would be, I want to associate that concept with my pictures, right? Then I would like to fine tune it. And those things work very well, right? But if they already have an existing concept like cat, right? And you're trying to manipulate that concept, that's slightly tricky, right? It's not going to get great results.
All right. Yeah. Thanks for that. Let's. We have another one from Zoom here. I'm going to bring this up on screen from Venkatesh on Zoom. If I fine-tune clip with a custom data set and use detailed textual descriptions of species or genera, could it potentially identify organisms at the taxonomic level? Interesting question.
Yes, it could. And that is what people use it. Out of the box, it won't work, right? So you have to fine tune it. I frankly don't know what would be the success rate, but because it is used, it's just because it may work doesn't mean that it should be used, right? If you want to do fine-grained image classification, that's the term, right? If you want to find different species of birds, for example, which look very similar, you want to tell them apart. The right architecture to use is fine-grained image classification. Search up these using that on Google, and you will find the right architecture to use, right? Which focus on these small differences between things, right? So that would be the right thing to use.
Okay, yeah. Dronzer says thanks there. We've got just a couple minutes left. I'm going to use this time to go ahead and share my screen with a new tab open here. So we've got another OpenCV competition here with our friends from Hackster. Let me go ahead and minimize Satya and bring in my screen share before we drop off here. There we go. And we'll go ahead and hide this. Yeah, so our friends at Hackster, the official community platform of OpenCV, have a new competition running right now, the Edge AI Earth Guardians. You can go to hackster.io/contest to see this. I'll also bring up a QR code on screen. You can scan that QR code, go to the official webpage, and register as a participant to win some pretty sweet prizes here. See the launch video narrated by yours truly here on the website. Registration is open from now until July 29th. So you still have plenty of time to register, but go ahead and get in there now. There's 116 participants currently. That means you have a pretty dang good chance of winning some of the top prizes here. This is all about ways to make a difference in the world, protecting our natural environment and the ecosystems around it, such as wildlife anti-poaching, forest health monitoring, marine ecosystem monitoring, stuff like that. Next, PCB is sponsoring $500 in manufacturing vouchers to 30 applicants for their projects. If you hit the go to the official webpage here and then tap apply for hardware after you register, you'll be able to ask for $500 in free manufacturing credits from Next PCB, makers of high quality short run printed circuit boards. And yeah, the top prizes here are a paid trip to Taiwan to present at the Edge AI Foundation event in November 2025. Never been to Taiwan. Seems like a really beautiful part of the world. You ever been to Taiwan, Doc? No? Oh,
No.
all right. Best,
No, not
and a
yet.
$2,500 award as well for the grand prize. Best board design will also be flown out to Taiwan. Best Edge AI technique and best applied solution, best education and social impact. Got some really great judges for this competition. Ginger always finds some of the smartest and most interesting people in the community of makers and hardware and software creators out there. So go register as a participant. It's absolutely free to register, and you can win some sweet prizes, including a trip to Taiwan. Who doesn't want to visit Taiwan? It seems like a great place. So Doc, why don't you go ahead and take us home here? Let me turn off my screen share, and yeah, go for it.
Well, thank you everybody for joining. I hope that this tutorial was useful. And if you want more of these, please let us know. Send an email to phil@opencv.org telling us that you would like to get more of these tutorials. Right? We have different formats for our live OpenCV Live, and one of the formats is this tutorial. If a lot of people ask for it, we will do more of these tutorials. Right. And watch out for our VLM Kickstarter. It is still about a month or so away, but it is going to be a great time to basically get a course for about half the price.
Those early bird prices, folks. You want to get on the Kickstarter page as soon as you can. Be the first one to know about it because it's a big savings, and you get the same course as everybody else for about half the price.
Yeah, and thank you so much, Phil, for organizing this. Nothing went wrong.
So far,
That's
so
great.
far, so good. Yeah. All right. Take care of yourselves out there, folks. Take care of somebody else if you can, and have a great day wherever you may be. We'll be back next Thursday, 9 a.m. Pacific time, same bat channel. We will see you then.